What's up everyone? Welcome to my talk. Today I'm going to show you how to fuzz the web for mysterious bugs. First of all, I wanted to thank Ben and all the NahamCon team for having me here today. So I'm André, aka OXCCB, aka Master of Mystery. I'm a co-founder of Ethiack. I'm a professor of ethical hacking in the University of Porto. I'm a bug bounty hunter and a former captain of the XSTF CTF team. So for today, we are going to take a look at user input validation problems, regex quirks, and then I'm going to show you how to fuzz regular expressions in a black box manner to uncover simple, mysterious bugs. And finally, I'm going to show you some real world examples of this. So it all started like 3 years ago. We had this endpoint that would redirect to a validated URL that needed to be part of a subdomain of example.com, and we wanted to redirect to an attacker-based domain, evil.com in this case. And if we manage to do it, we'll be able to exfiltrate also another parameter, which will be a secret token from a user, and then we could perform account takeover. The problem is that the regular expression in the backend was pretty locked down and we couldn't exploit it, or could we? So it all starts with user input. So most modern web applications or APIs and other types of applications rely on user input validation. And this is usually carried by regular expressions. In this example, we have a regular expression for email addresses, and as you can see, it will not match aa.com, but it will match a@a.com. And then we also have sanitization, which is basically responsible for escaping the user input, so we can prevent cross-site scripting and template injections and so on. And we also have normalization, which is basically responsible for making the user input consistent and avoiding duplicate data in most cases. For example, avoiding duplicate email addresses and so on. And we also have different behaviors in different programming languages and libraries, as you can see here, for the same input. So there are problems with validation. Regular expressions are widely used to validate the parameters, as I told you, and the developers are not testing those well enough. They copy paste them and they don't really know regular expressions. They copy those from Stack Overflow, GitHub, and other sources, RFCs, and so on. And sometimes testing code exists, but it's specific to a subset of the possible cases in terms of user input. For instance, the previous regular expression will accept special characters in the email address, and that can lead to problems later on the application, depending on how the email is processed. And another recent example is GitHub Copilot. This is a function generated automatically by GitHub Copilot in Python, and it's vulnerable, of course, because the URL is provided by the user and the domain is provided by the developer, for example. And we have two possible bypasses here. So the domain is basically formatted into the regular expression as example.com, and the dot will not be the actual dot character. It will rather match any character on this position between basically on example.com. The dot will let other characters go through, as you can see in the first two examples. And even if the dot was escaped, we could also bypass it in the open redirect scenario or SSRF scenario by putting an hash symbol or a question mark. So all those URL inputs will go through. So basically, we have the $sign as well in regular expression. And in my research, I was able to find something interesting. So the common description of the $sign asserts a position at the end of the string. If it's not present, we can basically provide an input and insert an arbitrary number of bytes after the end of the regular expression. So it needs to be used to assert the end of the string. But the common description of the $sign also says that It also asserts a position at the end of the string or before the line terminator right at the end of the string. So basically it should mean that we can have a new line character right at the end of the string and it will still match. So let's take a look on how the core libraries of well-known programming languages deal with this description. So JavaScript has this behavior, so it will match only the first input you see here with 3 A's, and it will not match with a new line or with a new line and digits after that, for example. And Python will accept 3 A's and a new line at the end, which is rejected by JavaScript. And Ruby, it's even more interesting because it will match anything, like it doesn't care what is after the new line, for example, it will still match the original input. And one of the problems here is that developers code these validations usually like this. So we have this input, we are going to match through a regular expression, and then the original input will be processed. And that's not a good way to do it, and that could open the door to weird bugs, because the developers should be extracting the match data you see here, and then pass it on through the rest of the code. And so to sum it up, as you can see in this table, we have JavaScript allowing only the first case and the Ruby allowing 3 of the 4 scenarios. So let's take a look at the technique I call REcollapse to fuzz and uncover these weird bugs. So it's all about probing the unknown. So the mindset here is about giving a lot of unexpected inputs into a black box. So we don't have the code, we don't know what regular expressions are being used in the backend. In the front end, we'll be able to access them, of course, but in terms of backend, we have no access. So we want to provide unexpected inputs, different inputs, and take a look at the responses. We get back weird behavior sometimes. We can try to understand what are the difference in terms of response codes, what are the difference in terms of response times and lengths and so on. So if we do this multiple times, the black box will start revealing information that we can use. So the REcollapse technique is about identifying 3 key pivot positions. So we are going to identify starting and termination positions, separated positions, and normalization positions that I'm going to show you after this. And then the idea is that we are going to fuzz all these positions with all possible bytes and analyze the responses. So in the first scenario, we should identify the starting and termination positions. And then we are going to try to understand if the regex is basically asserts the start of the string or the end of the string. And then we are going to understand what are the separator positions and fuzz them as well. This usually works because those are key parts of regular expressions that basically go to different groups of matching, different matches. So basically the idea is to pick these positions around special characters usually. And then we also have the normalization positions. Usually vowels work better in with most libraries, but this doesn't mean that other characters could be normalized. And in fact, a lot of characters can be normalized, and I just launched as well a normalization table that you can look and play with it and try to understand if your input is being normalized in your bug bounty scenarios. So these positions are typically vowels to increase the success of it, but we can pick other characters. So the idea is that, okay, we identified all these positions, and now we are going to fuzz all positions from 0 to FF. So we are going to try to, and we are not going to fuzz all the positions at the same time. That will basically explode the number of payloads that will need to fuzz with all the possible combinations. We are going to do this one by one, and that will reduce the complexity of it. So let's take a look at some examples according to the input we want to fuzz. So we have URLs, we have email addresses and usernames, which are basically critical account identifiers. And we usually have regular expressions for that because it's all about preventing the bad input in the first place. But that doesn't necessarily mean that later on we can have vulnerabilities if inserting like special characters and so on was possible in the first place. And also for HTML, for example, in terms of XSS, in terms of web application firewall bypasses, we can also try to fuzz with all the possible bytes in all these positions and try to understand what is not rejected. And what goes through, we can take a look at it and understand what would trigger, for example, an XSS. So it will always depend on the scenario that we are trying to exploit. In the case of SSRF, you would basically fuzz it and basically be listening for requests on your own server, for example, and try to understand what original input has led to that request, for example. And to make all of this easier, I launched the REcollapse tool. So it's an helper tool capable of generating inputs according to this rule. So basically the tool won't actually fuzz the endpoints. It will rather just generate inputs according to these rules, and you can basically use it to whip burp, intruder, for example, or other fuzzing tools we all use, such as FFUF and others. So it's available on my GitHub, so feel free to play with it, and it supports multiple fuzzing sizes and encoding. So basically, let's say that we didn't get any result, we can increase the size and fuzz like 2 bytes at the same time, and that will lead to a slow fuzzing process. It's gonna take a while, but sometimes it will result in very interesting scenarios that were supposedly impossible. In terms of encodings, you can also pick if you want to URL encode those bytes, if you want to use them with JSON-based body application, JSON bodies, or URL encode or in a raw format as well. So let's take a look on how we can use the REcollapse tool in a simulated scenario. So this demo is based on a real scenario. We have a logged in user that wants to log in to another application belonging to the same company. We hit yes, we take a look at the requests, we send it to repeater, and we try to play with it. So it generates an authentication token for a URL parameter that we provide. So our goal will be, okay, well, let's try evil.com. It doesn't work. Let's try just example.com, for example. It works. We can try HTTP as well. It also works. If we try .evil.com, it doesn't work. We can try a net symbol as well, like typical bypasses, and those doesn't work. So the idea about the REcollapse tool is to automate this fuzzing, as I told you, and to find novel bypasses. So let's try to use it and pass it like the input, an input that works, and we want to fuzz it, for example, as a starting point. It will generate something like this with all the possible byte combinations in multiple positions. All right, so we can also pass it as a word list to FFUF or other tools. In this case, we'll be excluding the 403 response code, and basically we'll get these results. So the first one is not a good candidate because it's like a slash, percentage to F is a slash in the end of example.com. It will break the domain and we cannot redirect to a domain we own. And then we have this one, the percentage for 0, which is the @ symbol. All right, so let's try to go from here and put it like at evil.com and try like some variations on these to see if we can bypass this validation. And after a while, we can see that we have example.com at evil/.com. So this is the perfect candidate because if we go here, it will basically just go to evil. So it will go to perform this redirect, and then the host will be evil/.com. So how we can leverage this at this point, it should be pretty easy, right? Because we can just pass like a decimal IP address, for example, because we understand we cannot have a dot in there. So basically, if we hit send, it will basically redirect to to this host, which is basically IP address I control and as a web server. And finally, it will redirect to actual evil.com, but the token will be already stored in the logs of my web server, allowing me to perform account takeover with interaction to victims that I can send this URL. All right, so how to find mysterious bugs with this technique or with this tool? So basically, we should look for anything that is validated, it's locked down, it's like sanitized, normalized, used in queries, and so on. So we want to find something that is apparently impossible. And basically, if we look into it and we try to apply this technique and fuzz it, this will actually open the door to mysterious bugs in hardened targets. So the process, and this is more like the methodology itself, it's about setting a goal in the first place. So let's say, okay, we want to have zero interaction account takeover on example.com. So we are going to pick our target field that we are going to look for weird behavior. So let's pick the email address, which is an account identifier used to log in multiple endpoints or applications or even subdomains of the target we are analyzing. So we are going to identify all the flows that consume the email address, and in every endpoint, in every subdomain, in every flow, we are going to use this technique. We are going to fuzz it. And then we are going to analyze all the response codes. Do we get anything interesting, any successful response, any 500 response like internal server error and so on. So, and we can try to write down and answer some questions. So is a regular expression always the same in all the endpoints? Usually not. Like even like in, well, like mature targets and hardened targets, it's actually very funny because the developers use different regular expressions in different endpoints. And this could lead to very interesting stuff. So after analyzing the response codes, we are going to pick a weird byte that went through in one of those positions. And then we'll go through all the flows that we identified in step 3, which is basically all the flows that consume this parameter. So we can try, this is just an example for account takeover. It's recovery, endpoints, login, sign up, OAuth, single sign-on, email change, confirmation, and so on. So it will always depend on the target field we are trying to exploit. And hopefully, so this is basically what I call the moment when we find a mysterious bug. So we obtained an error or a weird behavior, and then we are going to try to realize the impact or an attack scenario for that weird state we got our account into in this scenario, or we got the application into in this scenario. And if not, if like nothing is like apparently buggy, we are going to go back to step 5B or 1 or 2. So we are going to pick another weird byte that went through and gave us another response on a specific endpoint, or obviously we are going to change the field or even the goal, of course. So that's the methodology to uncover this type of weird stuff. So let's take a look at some real world examples. If you want to take a look at more examples, you can go through my GitHub and the REcollapse GitHub, and you'll have more examples of this. So the first one is a weird web cache deception that I was able to find while collaborating with Technogeek a few years back. So basically, we had this redacted.com target, and we wanted to basically understand if we could trigger any sort of web cache deception, because in this endpoint, WP-JSON v1 user, we could get an API token from a victim. In this case, from ourselves, but we wanted to take it from a victim. So, of course, we tried like .css, .pdf, .js, that could basically be cached somehow, depending on the configuration of the load balancer or the web server and so on. But we got 404 responses for that. So we were playing with this technique, and basically we just wanted to fuzz it. And basically we realized, okay, so caching rules are usually regex based, and basically a static extension is not enough these days to perform the web cache deception. So we actually need to get the correct content type in the response, and if we make it work, basically we might be able to have a web cache deception a scenario and exfiltrate the cache to response from a victim. So let's fuzz it. So we tried to fix this dot extension in this endpoint, and we fuzzed it on this separator position before the dot. So we fuzzed from 0 to FF, and also well-known extensions, and after a while it returned 200 with percentage 23, which is basically an hash symbol and a question mark as well. And in response we were able to see, okay, so we have an H35 Xcache it, and we noticed it because we have a different response code but also a different response length. So we were able to trigger a web cache deception with percentage 23 or 3f.pdf on an API, which was like mind blown at the time. So basically we can send a link to a logged in victim, and the victim will request this URL, and if it's logged in, we can just access the cached content from another location and steal the API token, and boom, we get access to the victim's account through web cache deception. Another example is a zero interaction account takeover through OAuth. So this one was on Shopify. I'd like to thank Shopify for allowing me to disclose this one. So basically Shopify offers a sign up login with Shopify OAuth mechanism, and basically the scope will include email address to log in multiple applications, and it will be consumed to create an account on other applications. And one of those that was in scope for a specific live hacking event was taller.app. So the email address didn't need to actually be verified to create an account, but if the email already existed, we couldn't log in or sign up on Shopify. So we needed to sign up on Shopify with the victim's account, and we couldn't do it. So let's fuzz the email change request on accounts.shopify.com that is basically responsible for allowing users to manage their account. So we try to change our email to the victims by using like new lines in the end and special characters and so on. So no weird characters were allowed. But on the sign up request, and this was a slow fuzzing process because of, like captchas and so on. So on accounts.shopify.com, when we were signing up, we could basically use this weird I character, for example, which would be normalized, and it will go through. So the actual email address on accounts.shopify.com will be the actual one, like without being normalized. But when we logged in with Shopify in this weird state on the third-party application through OAuth, we were able to achieve a successful account takeover without any interaction, as you can see on this video. So this is the victim's account, and we are not able to sign up on Shopify with the victim's email address. So we open a new session, we go to the third-party application, Tyler.app. In this case, we are going to sign up with Shopify. Then we are going to sign up with an email which is allowed with this weird A character. And after we create our account, we'll be redirected to the target application, and it's very simple. We'll just be logged in the victim's account. So yeah, this was a fun one and simple one that I was able to find with Fisher like 2 years ago. And after that, we realized that OAuth SAML flows were basically passing all these critical account identifiers to destination applications, and normalization is often used in these flows to make the input consistent, and it makes sense. The problem is that the OAuth provider application, like the parent application, the big target, if there's like one endpoint that would accept like weird input characters that will not be normalized in the first place, this will be pretty bad, because the destination, in the destination application, we will be able to take over accounts without any interaction. So some takeaways to sum it up. So developers, always test and fuzz your regular expressions or rely on well-known libraries. And even well-known libraries, like if you fuzz it, just try to see the results and I'll bet that you'll be surprised. And simple modifications, and this is the major takeaway here, is that we could go towards complexity, but the idea is that simple input modifications can result in great impact by fuzzing, flipping, or adding bytes, basically. And so black box regular expression testing is still not very touched. It's creative and manual work, so go for it. And you can also, of course, like automate the fuzzing part by relying on the REcollapse tool or other methods. And basically, the regular expression behavior can also reveal information about libraries, programming languages, the backend, endpoints, and so on. So basically, the idea is that if something is being validated and you can bypass it, think about the impact if it's not clear instantly, and you'll be able to see the big picture. So thank you, everyone. I would like to shout out all of these people and teams. I couldn't list everyone that collaborated with me, but thank you so much, everyone, for being such a good fellow hackers for the past couple of years. So thank you, everyone, and let me know if you have any questions.